presentation on enhancing the design workflow within SOLIDWORKS using generative design. My name is Sashi Satambaram. I am a simulation technical manager here with the North American SOLIDWORKS team, and I will be your presenter for the day. So before we get into the presentation, just a few housekeeping items. The best way to view this webinar would be in full screen, and to collapse this panel that you see on your right left side of your screen, the GoToMeeting panel, just click on the small orange button and that will collapse the panel. However, if you have any questions, there is a questions panel that you can type in your questions, and we'll get to the questions at the end of the webinar today. Time permitting, and if I don't get your questions, I will follow up with an email to your to the answer for your questions. Okay, so to start off this this presentation today, I wanted to ask the question if you've ever heard of the designer's block. So a lot of you might be familiar with the writer's block, where if you're an author, if you write articles or blogs, either before you start or after you've written a few chapters or a few paragraphs, it's just you experience this block of ideas where there's no more ideas coming to your mind, and it starts to get very difficult to continue writing your story. Well, there's a very similar experience with the designer, where we call it the designer's block. And I remember myself when I was doing a lot of design work, I would experience this every now and then, and it typically happens in two scenarios. Number one is before you start your design, where you are given a very complex set of requirements, and you have to now come up with an entirely new design, and you tend to go through this 5 stages, or more frequently when you experience design changes, right? So a lot of times you might spend a few weeks or a few months on a certain design. You captured the design, and now you're required to make a design change. It becomes very difficult because you've spent all this time, you've almost boxed your creativity into the design that you see in front of you, and it's now very difficult to think out of the box. So a lot of times you experience these 5 stages in the sense that, typically, when you start the new design, you say, you know what, no problem. We're all engineers, we're all designers. We like to take on challenges. You say, no problem. Then, we design, we go through that process, we get very angry. We say, the design doesn't make any sense. Then maybe we start bargaining, right? We say, oh, maybe no one will realize this design doesn't really meet all the requirements, doesn't really work like how it's supposed to. Well, the problem is, as designers, as engineers, it's very difficult to just close one eye to things like that, right? We like things to work the way it's supposed to work. So then we get into that 4th stage where we're starting to contemplate if this design is even going to work. And then we go to that 5th stage where we say, well, that design is just not going to work. And then we go back to the drawing board, go back to the whiteboard. What a lot of people don't understand is this is a typical process, right? When we go through our design iterations, this is very typical, right? We start with the design, we go through the process, and then we come to a conclusion that it doesn't work, and then we go back, we keep going around and around until we find that design that works, that's robust. Well, what we're proposing here at SOLIDWORKS is let us help you get over this barrier with some of the tools that we have within SOLIDWORKS. A lot of times we can use or reuse the existing data that you may have, especially in situations where you're redesigning a component. So Topology Study it was introduced in SOLIDWORKS 2018 and is a fantastic tool. It's a generative design tool that will help you think outside the box, come up with designs that maybe you've never even thought about, using the requirements or applying the design requirements for that part or component. So topology optimization is part of our simulation offering. And for many years, especially with SOLIDWORKS, we've advocated running simulation in parallel with the design process. It's the best way to come up with optimized designs, right? Validate your designs as you're designing, as you're changing features, as you're adding features. Ensure that any features that you're adding or removing is not is keeping the part within its design requirements. And this has worked for many years, and this is a great process. But what we are advocating for tomorrow is to start innovating that original design. Start thinking outside the box, using tools like Topology Study to innovate better designs from the get-go, and use simulation as a confirmation, right? So by combining the generative design process early with the design process, we can start to create extremely optimized parts in very early design stages, and using simulation to confirm that those parts are strong, are deflecting minimally, and are within an acceptable factor of safety. So just to give you a little bit of overview on Topology Study, Topology Study uses a minimum mass component optimization, where again it takes into account your stiffness criteria, so it ensures the part is still strong enough, and tries to remove as much material from the part to reduce the weight. So it delivers minimum mass solutions. For SOLIDWORKS Topology Study, we allow multiple simultaneous load cases. So forces that might be coming in from different directions can be coupled together within a single study. It is constrained by stiffness. So again, keeping that strength integrity intact. So just not removing material just for the sake of removing it. However, removing it critically and ensuring the part is still within the design specs. In addition to constraints and goals, you can also add manufacturing process considerations to better suit the optimized part for the manufacturing process that you will choose this part to be manufactured down the road. So it could be 3D printed, it could be CNC machined, it could be injection molded. Using some of the different manufacturing processes that we have, you can change the optimized shape to better suit that manufacturing process. So this optimization tool that we have, again, it's new in 2018, and it's powered by the Tosca solvers from Simulia, which is from our parent company, Dassault Systems. So it's very powerful, and it's fully integrated into the SOLIDWORKS user interface. So basically, it's taking the best of two worlds, right? It's taking SOLIDWORKS, which is the best 3D CAD modeler on the market, and it's taking Simulia, a very powerful simulation solver, and it's combining those two elements into a single interface for SOLIDWORKS users. So the typical workflow using Topology Study is you always want to start with that initial design validation. So what we are proposing is not to remove that initial design validation, but to ingrain it with Topology Study. So you always start with that initial design validation. And the main reason to do this is to ensure that you do have leeway in terms of being able to remove material. You need to ensure that the part that you have to begin with is below the yield strength, is deflecting minimally, it's below the factor of safety. It's way above the factor of safety, to ensure that, or to confirm that this part is possibly has been over-designed. The next step is, if you want to define your topology goals and constraints, let the simulation run to give you the best results, showing you areas where you can remove material. And of course, at the end of this workflow, it's always a good practice to run another validation to ensure that the results that you're getting from the topology study is within the design requirements. It's able to withstand the forces that will be applied to it. So I have two examples today, and I'm going to start with a subtractive manufacturing example. So the goal is, with this tool, you want to be able to use it in both subtractive and additive manufacturing. So with subtractive manufacturing, the idea is that you want to try to keep the shape of the original design as much as possible. And you want to try to remove material to possibly reduce weight, reduce weight, or possibly turn this part into an injection molding part down the road. So the example that I have today is, it's a very simple bracket, but it does have a unique shape to fit its fixtures. Now, because of its unique shape, we want to try to retain its original shape. We're trying to reduce weight. That's our goal here. It has to be, we have to be able to machine this on a 2.5 axis CNC machine, because we are in a prototype stage. So perhaps we're doing this in-house. And we need to consider the fact that down the road, we might want to injection mold this part. So let's switch over to SOLIDWORKS and take a look at this part right here. So as I mentioned with the workflow, you always want to start with a static analysis. So what I have here is very simple setup. It is a plain carbon steel material. It's fixed at 3 locations. I have a 100-pound force acting right in the middle on this face, downwards. And running the analysis shows us that the stress distribution for this part is anywhere between 1500 psi to about 2800 psi. What's most important about this results is that it's way below the yield strength. Looking at the displacement, 0.002 millimeters, almost negligible. And last but not least, the factor of safety, the minimum factor of safety we have right now is 11, which means this part has clearly been over-designed for its use, for its operational use. So these signs within the static analysis shows us that we might be able to remove material without causing any type of failure for this part. So to run your topology study, it is within the simulation add-in. And if you select a new study, you'll see topology studies right here. However, going back to that workflow, considering that we've already ran a linear static analysis, the easiest way to set up a topology study is to simply right-click that static analysis and just say copy study. And you can actually target this study, this original study, into a topology study. And I'll say OK. And you will see that the material, fixture, and forces from that static analysis has automatically been transferred into my topology study here. So all that I need to set up for this analysis is my goals and constraints and my manufacturing controls. So we'll start with the goals and constraints here. So we have 3 options, 3 three types of goals available within topology study: best stiffness to weight ratio, minimize mass displacement, and minimize mass with displacement constraint. Now, depending on your design criteria or your optimization criteria, you can pick any one of these, but the recommendation is to always pick the best stiffness to weight ratio, because what we've seen is in most cases, the best stiffness to weight ratio gives you the best results. So I'm just going to select that right now. And once you've selected your goal, you can set up to 2 constraints. So my first constraint, I'm going to say it is a mass constraint. I'm going to say that I would like to remove up to 75% of material. Now, just so you know that when the analysis run, it will not, or it may not remove up to 75%. It will remove up to a point that it is still below that yield strength criteria. Setting up 75% is a goal that the software tries to achieve during the optimization stage. You can set up a second displacement constraint where you can specify that the optimized part cannot displace over a certain amount. Now, considering that the displacement amount that we had for this original part was so low, was almost negligible, I'm just not even going to include the second constraint for this analysis. So I'm going to say OK here. Now, the next thing we have on this list is manufacturing controls. So as I had mentioned, this shape of this part is unique. So I would like to preserve the shape of this part. So by selecting Add Preserve Region, I'm able to quickly select the outside faces of this part. And to do that, just right-click, select tangency. They're all tangent to each other. So that's a quick, easy way to select those faces. And we also have the ability to check a preserved area depth to add some thickness to the preserved region. So in cases where you're running a topology optimization and there's certain features or walls that you like to retain, and you don't want the software to remove those faces, you can use the preserve region tool to do that, to control which faces or which geometry will be removed. Now, in this example, you can also specify a geometry preview. So you can see here how it's creating that preview for me right now. Basically, it will retain up to 1 millimeter of wall thickness for this part. For this specific example, though, I'm actually going to uncheck this because I would like the software to calculate what may be the best wall thickness here, depending on the optimization. So I'll say OK. Now, besides manufacturing, besides the preserve region, we also have the ability to add a thickness control. So for example, if you bought a part, a stock material with a specified thickness, you can specify that. So the optimization won't remove material along the thickness. You can specify demold direction. So if this part is eventually going to be stamped or casted or injection molded, you can specify which direction the mold will be removed from the part to better shape your optimized parts. So I'm not going to add any of those manufacturing controls for now, just to see what we get in this first iteration. So at this point, we're ready to run the analysis. And I pre-ran this analysis so we can take a look at the results very quickly here. And we can see that the optimized part, we're starting to get a shape or we're starting to shape it out. It's clearly removed some areas right here, but then as we dive closer into this part, we can see that there are some holes, some pockets that the analysis has calculated as areas we can remove. Now, while this part may be okay for 3D printing, it's not so much for CNC machine. right? I mean, we could certainly just ignore these holes and just focus on these larger areas and shape it ourselves. But why take on that work when the software can do that for us, right? So by simply adding some manufacturing controls, we can actually create a much better shape from this optimization study. So for your demo directions, we have 3 options: mid-plane, so again for like injection molding, pull direction only could be for casting restrictions, and we also have a pull in one direction for stamping. For this example, I'm going to say mid-plane in both directions. And by checking this option right here, determine central mid-plane automatically, it will, by selecting that edge, it will automatically specify the midpoint of that edge for us. Makes it a little bit easier. Say okay. And let's take a look at our results when we add that manufacturing control. So just adding that one demo control gives us a much better shape. And you can see now those holes, those pockets are gone, right? It's been removed. So this part is a little bit more suitable for a CNC machine or possibly an injection molding part or injection molded part down the road. So one other thing with parts like this is typically at the fixtures you would have a what we call an ear or a step down for where the bolt might sit. So introducing design changes is very easy when you're navigating within SOLIDWORKS itself, right? So I have a configuration here called design change, and all I've done is created these steps right here. Now again, using that copy study, we can just easily copy the original study, change the configuration here to design change, which is the configuration with this step, and say okay. And now you can see that not only the material, fixtures, and loads have transferred, the constraints and manufacturing controls have also transferred over. So for this analysis, it's as easy as just right-clicking and hitting run to rerun the analysis and see what your new results would be. So let's go ahead and take a look at this result for this part. I'll just go ahead and hide the simulation notifications, and you can see now this part is shaped even much better. With this step down here, it has created some walls in this area, and you can see these cutout are much more rounder, which is most suitable for CNC machine. So when you have a part like this that we've retained the outer shape, and all we have to do now is just remove these areas, it's as easy as sketching them in and using extrude cut, right? So looking at my final design here, you can see that this is a part that can easily be cut on a 2.5 axis CNC machine. And by adding some draft to this wall, this part can down the road be injection moldable without any issues. So that's the first example. So the second example that I have for you today is additive manufacturing. And I'm going to go through this example fairly quickly. It's very similar in terms of the setup. So going to this next part, we have a table mount. So this table mount sits underneath the table, and it allows this table to slide. So think of a table in a motorhome or in a dorm, in a small confined area where the table can slide from one side to the other. And this part, this mount, sits underneath the table. This part right now is being injection molded. You can see the drafts on all the walls. However, the problem is the mold for this part has been damaged. So the company now has decided, is it a good idea to spend hundreds of thousands of dollars to recreating a new mold, or is it possible to just 3D print this part, right? And spend that money buying a 3D printer, which can be used in many different areas within the company. So using this virtual environment that we have, which is SolidWorks, we can easily try that out, right? Without having to buy the 3D printer, without having to create the mold, we can just simply try it out within SolidWorks to see if this is going to be a good, suitable change for the company to take. So the goal is to reduce the manufacturing cost to see if this part can be 3D printed. And because now we're considering 3D printing, we can even think about the fact that, hey, can we completely change this design? Possibly, right? We don't have to abide by the injection molding rules anymore. And a bonus to this is, can we reduce the weight if possible? So let's switch over back to SolidWorks. If I can find it. There we go. And whenever we are considering a part that may be 3D printed down the road, a good step is to always start with what we call as the block design. The block design only keeps critical features for fixturing. So for example, this hole right here is where the mount is fixed to the bar that's attached to the ground. So we need to retain that hole within the block design. The next thing that we have is these features, these 4 features, is a feature that connects to the slider that allows the table to slide back and forth. So these 2 features I have kept as part of the block design, but everything else is covered. Why? Is because I'm allowing the topology study to remove as much material as possible and come up with a completely different shape, a shape that's going to be within the design requirements, but possibly a shape that I've never thought about, that I would have never even considered as part of my design process. So if we take a look at the topology study here, I fixed this face. In terms of forces, I've applied 100 pounds of force. So basically, imagine a small kid, or if you put plates and food on a table, up to about 100 pounds, distributed evenly across these 4 faces. For my goals and constraint, I've done the same as I did in the last example. I just said I'm going to try to remove up to 75% material. And for my manufacturing controls, all I've done here is preserve 2 things: the hole and these 4 features with a preserved depth area of 5 millimeters. So if we check out the preview, we can see that these features will be kept in my optimized part. Everything else I can remove if it's not critical for my final design. I don't want to add any other manufacturing controls because, like I said, I want to give the study as much freedom as possible to come up with any possible shape that I could possibly 3D print down the road. So with that said, let's take a look at our results. Let's give it a second here. So this is the final shape that the topology study returned after running the analysis. It is a very interesting shape, and using some of the tools within, some of the design tools within SolidWorks, such as surfacing tools, or using some of our partner products that allows for sub-D modeling, we can come up with a very, very cool design based on this shape. But just so you know, within SolidWorks itself, within Topology Study, you can export these models as a solid STL, a surface STL, or a graphics STL. And within this or the next release, we will have tools that will allow you to reuse this imported geometry to create solid bodies very easily. So let's take a look at the final design that we created with just the SOLIDWORKS design tools. So this is the part that we can now 3D print. And just so you know, if you have a part that is going to a 3D printer, we do have some tools to check if this part is 3D printer ready. If you go into your file, print 3D, you do have some tools right here that will allow you to check your 3D print parts before sending it to a 3D printer. So just so you know, if you like what you see today in terms of these topology study tools, you can actually try it right away, right after this webinar. So if you go to solidworks.com/trials, it will take you to this website. It is our online product trial. So no downloads required. You can log in if you have a SolidWorks ID, or you can sign up for SolidWorks ID, and you can hit the ground running with this tool today. So think about some of the tools that or some of the parts that you have designed maybe in the past. Maybe you have over-designed some of these parts to ensure that it doesn't fail in operation. Perhaps those parts can be redesigned. I would challenge you to take those parts and pop it into this product trial and see what type of results you may get. In addition to that, again, if you like what you saw today, we are having an event. So the SolidWorks technical team is going on the road, and we're having live events where we're going to be showing tools like this and many other tools within the SolidWorks brand, even outside of simulation. And it's going to be a live event in 8 locations. So if it's a location close to you, go ahead and sign up today because seats are very limited. If you don't see a location close to where you are, no problem. We are also going to have a virtual tour after these live events. So please still sign up for the virtual tour. So before I go to questions, I just wanted to wrap up the topology study. Exponential weight reduction. That's always a huge bonus if we can reduce weight. It might not always make sense, right, in the real world. It might cost too much to cut out material from a CNC machine. At that point, we have to weigh the cost of the part versus the operational costs. But in a lot of cases, having a part with reduced weight can affect the entire system, right? And being, again, in a virtual environment, you can easily test that out. You can create organic designs. So this is a new space, right, for all of us in the design world. And having tools like Topology Study helps you design these organic shapes, right? Because we're no more in that linear world. Organic shapes can be anything, and it can become challenging. So having tools like this put some rules and regulations in place and helps us come up with really good, robust designs. And last but not least, when we use tools like this, we want to try to cover additive and subtractive manufacturing, but putting some thought into how this part may be manufactured at the end will help you define a much better shape within your topology study itself. So I've gone over my 22 minutes, but I'm going to spend the next 5 minutes to answer some questions. We have a lot of questions coming in. So the first question is, how long does it take to run the simulation? So it's a little bit as long as a linear static analysis. Again, it depends on how much criterias that you set, what type of mesh you're using, how complex is the geometry. So it can vary. it is within an acceptable time range. So next question I have is, can you explain again how to go from a topology part to a manufacturable part? So once we have the topology optimized design, it is an STL file. So it's either graphics, solid, or surfaces. Within SolidWorks itself, we can use that as a template and just design over it. If it's a surface or a solid, it's selectable faces. And we also have some additional tools that was introduced in 2018 and also will be introduced in 2019 that will help with that process, taking mesh geometry and creating solid geometry from it. Like I said, that we also have partner products, SolidWorks partner products. So if you go to our website, partner products, we have partner products that does sub-D modeling. So basically, being able to create very organic shapes easily. So you can take a look at those as well. So another question is, can it perform modal analysis as well? So once you have the shape, the final shape, you can run any analysis on it because it is just basically a SolidWorks part. So you'll be able to run a thermal analysis on it. You'll be able to run a modal analysis, frequency analysis. You'll be able to run a parametric optimization analysis on it. It is basically as part of any of the simulation offering that we have. Is it possible to run multiple configurations through the simulation at the same time? So we do have the ability to batch run. So technically it won't be run simultaneously. It can be run in parallel, so without having to control. So you'll be able to just run it. Let's say when you leave work at the end of the night, you'll be able to stack up multiple analysis and just run it. So that when you come back the next day, you'll have all the analysis completed. Let's see other questions we have here. All right, so those are the only questions right now. If there's any questions that I wasn't able to get to, I will email you as well. So again, thank you very much for joining me this afternoon. I hope everyone has a great day, and see you at the next webinar.